All right, so today we're starting chapters 16 and 17 in the book. It's on acids and bases. Feel free to start reading those chapters since we're spending not a lot of time on it. So, first thing we have to know, anytime a hydrogen ion is referred to, it's H+, and it's also called a proton. Hydronium ion is H3O+. It's formed by taking your hydrogen ion and adding it to water. So H3O+ is a hydronium ion. Strong acids and bases. We've already talked about those. These are the 6 strong acids, Bic pens. You can learn it like that. Or, so I brought no clean clothes. Also works. Whatever you do to memorize that. Strong bases are your soluble group 1 and 2 hydroxides. So they have to be soluble. So that's group 1, that's group 2. Also make sure you know that the group 1s are +1, so it just have 1 OH, and the group 2s are +2, so they have 2 hydroxides. And just in case you forgot, hydroxide is OH -1. All right, strong acids completely ionize to give the hydronium ion and an anion. So if you have perchloric acid, it ionizes to give you H3O+ and ClO4-. You can also see this another way. You will just see HClO4+, aqueous, and it can ionize into H+, aqueous, and ClO4-, aqueous. You can also see it like that. The water's here. Obviously, this H joins with the water to form the hydronium ion. Neutral, add an H+, it's now H3O+. Strong bases completely ionize to give the hydroxide ion. So you have NaOH, and it just decomposes into Na+, plus OH-. You don't have to worry about the water here. I just have it written. So it's similar to the strong acid equation. So a lot of the times you won't have that written there. Notice that these arrows are going directly to the products because they ionize 100%. 100% ionization. That's going to come in more handy when we do weak acids because they do not ionize 100%. There's a couple different theories here that we're briefly going to go over. Acids donate a hydrogen ion. Bases donate a hydroxide ion. That was okay, but what if you had something like ammonia? Ammonia is a base. Ammonia doesn't have a hydroxide to donate. So this theory was quickly replaced by the Bronsted-Lowry theory, where it says an acid donates a proton and a base accepts a proton. We discussed this way back in chapter 4, so hopefully it rings a bell. So now if we look at some equations, we can tell what's the acid, what's the base. Some species act as both acids or bases, depending on what they're reacting with. Acids and bases can be ions, and they can be neutral compounds. Let's mosey on to the next page. Lewis definition, I do not think you need to know that. It's just saying that the acid accepts an electron pair, the base donates one. All right, we're going to rely on the Bronsted-Lowry concept. So we need to identify the acid, the base, the conjugate acid, and the conjugate base in an equation. You have already done this a little bit. So a pair of compounds that differ by the presence of one proton, this is a conjugate acid pair. Make sure you understand how to identify these because when we do buffers, it's going to be a lot easier. So acids have conjugate bases and bases have conjugate acids. The acids and bases will be on one side and the conjugate acids and bases will be on the other side. Remember to the definition, acids give up a proton, the conjugate base will form the acid of the other side. Bases go from A- to HA, which will be the conjugate acid. What am I talking about? So let's look at this right here. We have HNO3. Look to see what it becomes on the other side. So HNO3 becomes NO3 minus. So what happened to this HNO3? It lost a proton. So that means this is your acid because it donated a proton. And let's see what this guy, it went from H2O to H3O plus. So this gained a proton. So this is your base. If you look on the other side, this was your base, this is your conjugate acid then. If this is your acid, that's your conjugate base. Another way to look at these, just reverse the reaction. What is this H3O doing? It's going from H3O to H2O if you're going backwards. So it's losing a proton, so that's conjugate acid. And the NO3 is becoming HNO3, so it's gaining a proton. So it's acting like the base. The left side you'll have your acid base. The right side you'll have your conjugate acid, conjugate base. So right here, we'll talk about that later. This guy right here, let's see what's happening. We have NH4. Is NH4 becoming H3O plus? No. Is NH4 becoming NH3? Absolutely. So how's it becoming NH3? It's losing a proton. So that's why this is the acid, and your H2O is becoming H3O plus, and how's it doing that? It's gaining a proton. So whatever loses a proton becomes an acid, whatever gains a proton becomes a base. If you need to look at the other side, just look at the reverse reaction. This H3O is becoming H2O, so that's why this is your conjugate acid. It's losing a proton, donating a proton, and this conjugate base is becoming NH3 to NH4 plus, and it is gaining a proton. That's why it's a conjugate base. This last one, again, it's the same type of thing, but this is a diprotic acid. Diprotic means two hydrogens. So these are going to have several different steps when it loses a proton. We're only looking at the first step. So here, this H2PO4 is becoming HPO4 negative 2. Oops, it's H2PO4 negative 1. So if you look at this, if you lose an H plus, you're now more negative. And that's why that becomes negative 2. So you're losing another H. What if they would lose another proton? Then it would end up PO4 negative 3. So because this lost a proton, it's the acid. The water gained the proton, it's the base. And you could look at the reverse action to see how this is the conjugate acid and conjugate base. All right, in each of these acid examples, notice the formation of hydronium ion. Hydronium ion means acidic. So it lets you know anytime you're producing that hydronium ion, it's going to be an acidic solution. All right, so this is just showing you what happens with the hydronium ion. It just says the H plus is riding piggyback on a water molecule, water is polar, and the positive charge of the naked proton is greatly attracted to Mickey's chin. Mickey being the water molecule. All right, this is Mickey's chin. We know this is partial negative, and we know this is partial positive. That's why it's attracted to the water molecule. All right. We can look at some of these other ones. Same type of ideas. NH3 is going to NH4, so it's gaining a proton, so it's a base. And H2O is going to OH negative, so it's losing a proton, so that's why it's the acid. You're probably thinking, well, water can't be acidic. It depends on what it's reacting with. We just saw in those 3 previous examples, water was acting as a base. Now in these examples, water is acting like an acid. It all depends on what it's reacting with. Just always follow your rules. If it's donating a proton, it's an acid. If it's gaining a proton, it's a base. And then do the reverse reaction to figure out your conjugate acids and conjugate bases. All right, anytime you form hydroxide, it's a basic solution. All right, stop the video, try to do these, identify the acid and conjugate base. And I'm going to do it because you can easily stop the video and try it yourself to see how much you know. HBr is going to be R. So HBr is your acid because it's losing a proton. NH3 is going to NH4 plus. It's your base because it's gaining a proton. So that was easy on that side. Let's go opposite. NH4 is going to NH3, going backwards, so that's your conjugate acid. And Br negative is gaining a proton to HBr, so that's your conjugate base. They're asking you what is the conjugate base of H2S? Well, that would be Br negative. What is the conjugate acid of NO3 negative? That should be NH3. And it's NH4 plus. That should be NH3. There. All right. Easy, right? So acids have conjugate bases and bases have conjugate acids. Acids only donate 1 proton at a time, so 1 hydrogen at a time. Monoprotic are acids with 1 hydrogen, diprotic have 2, polyprotic have 3 or more. Polyprotic bases accept more than 1 H. Those are like your anions with your negative 2 and negative 3 charges. Amphiprotic or amphoteric. Molecules or ions that can behave as either acids or bases. Water, anions of weak base or weak acids are an example. You can just look at those previous examples on the other page. All right. Acid dissociation. So this first part of these notes are all strong acids and bases, and I told you at the beginning that acids and bases, oh, I just realized that this was a totally different question than these. Sorry. They're asking you something different here. What is the conjugate base of H2S? So if they're asking for the conjugate base of H2S, that means H2S is acting as an acid. What would the conjugate base of that? Take a proton off, and it'd just be HS negative. So you would just lose a proton. So you're losing an H plus, which would result in a -1 charge. Since they're asking for the conjugate acid of NO3 negative, this means that that has to be a base. So that means it has to gain a proton. So add a H plus to that. So H plus NO3 minus, it would be neutral, and it would just be HNO3. Sorry about that. I didn't read that correctly. I'm trying to get through this quickly so you don't have a lot to watch. All right, so these ionization reactions, it's just simple dissociation. Dissociation means breaking apart into its ions. So go ahead, stop the video and see if you can write these ionization reactions, and we can go from there. I'm going to just keep on going. So HCl aqueous yields H plus aqueous plus Cl negative aqueous. All right, so I have them all written here. This is acid dissociation reactions, so you know for all of these you should be producing the hydrogen ion. So you just have to remove a hydrogen ion from every single one of these ions or molecules. This guy right here, you're removing an H+. It has a plus charge as it is, so if you're removing an H+, you're down to H3, and you no longer have a positive charge because it went right here. This one right here, again, you're removing an H+, so you no longer have 3 H's, you have 2, and it's no longer positive, it's neutral. This guy right here, it's a little bit harder to see, so just break it up into AlH2O5 plus HOH. So if you add these together, it's H2O6. Now what has to happen? You have to lose this proton right here, so you're going to lose that H+, and that's what we have right here. And if you're losing this H+, you're left with OH. So you lost a positive charge, so you went from +3 down to +2. Acid dissociation reactions. Okay, strengths of acids and bases. We said that strong acids and bases dissociate 100%. That means they have very large K values, which means they're producing a lot of ions. Lots of ions produced. So if you would have a strong acid dissociating, let's make a bigger beaker, such as HCl, you would have a lot of HCl ions. They'd all be HCl ions. Would you have any HCl in there? No, because it dissociated 100%. What if you had a weak acid, like acetic acid? You would probably have more acetic acid molecules together, H2O3O2, C2H3O2, too many O's, C2H3O2, sorry. But then you would have a little bit of ions, because they dissociate a little bit. Okay, if we wanted to do this with a base, it would dissociate 100% into its ions. And if you're talking about a weak base, you would have some of your hydroxide left in there. I don't want to draw that yet because I don't want to pick a weak base that is not soluble. Because if it's not soluble, it's going to stay as a solid, and it would just stay together. All right, weak acids and bases dissociate probably less than 15%. So their K is very, very, very tiny. All right, got these. Already talked about those. Strong bases, bond strength for the strong acids. What can you conclude about what do acids want to do? Acids want to lose their protons, right? Lose their protons, lose their H+. Look at the strength of this bond. It's strong. Is it going to be easy to lose this hydrogen off of this HF bond? No, it's going to take 565 kilojoules of energy. So it is more difficult to lose that H. That's why it is a weak acid. It does not lose its proton easily. These other ones, they lose that proton easily, so they're strong acids. Substances that lose the proton easily are strong acids. Something you also have to know, the more oxygen present in a polyatomic ion of an oxyacid, the stronger its acid within that group. Okay? An oxyacid is an acid with oxygen. So the more oxygens, the stronger its acid. But it has to be in the same group. So you can't compare acids that are not in the same group. First, notice that the H of the acid is bound to an oxygen, which you learned back in Chapter 9. When you're drawing Lewis structures for acids, the H is always coming off of an O because the oxygen is very electronegative and it attracts the electrons of the partial positive hydrogen. If you add more oxygens, that effect is magnified. Okay? So if we would look at this HClO4 and compare it all the way down to HClO, the more oxygens you have, the stronger the acid. What does this Ka value tell you? That tells you how much of it's dissociating. So if it has a large Ka, and Ka is just like our other ones. We had Kc, we've had Ksp, we have Ka, now we have Kb. And we even have Keq. A large K tells you that it's dissociating into its ions a lot. It's a strong acid. As you decrease the number of oxygens, your K value gets smaller, which tells you it's not that strong of an acid. It's not going to dissociate into its ions that much. You can look at the sulfate oxyacids, and you can also look at the nitrogen oxyacids and apply the same rules. Strong bases. These are your soluble hydroxides of your group 1 and 2 metals. We've already discussed them on the front page. The stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid. All right. So if we have charts, we usually have Ka or Kb charts to look at. Before I go down, just going to write. So, if Ka is large, it's a strong acid. What does that large Ka mean? That it's going toward the products. It's dissociating 100%. The equilibrium concentration, you're going to have a lot of H hydrogen ions being produced. How many? Well, it's going to be equal to whatever the strength of your acid was. Why? Because it ionizes 100%. If you're comparing HA, what is the conjugate base of this HA? Would be A negative. Your A negative is much weaker than your H2O. Strong acids have weak conjugate bases. Another way you could look at it is the opposite way, looking at a weak acid. I always remember it like this. Stronger acids lose their protons easier. Stronger bases hold their protons more. I think that's easier for you to remember than remembering all this. All right. That is it for strong acids and bases. Now we're going to get into the fun part of weak acids and bases. So I'm going to stop the video and start a new one.